As most of the enterprises are actually going to cloud, I would like to share our experiences in the journey of scaling these enterprise solutions on cloud from IBM. And most of you might have seen Hurricane Florence when it hit Carolinas last month. You can clearly see the test on the scalability of the weather APIs that are actually deployed on IBM Cloud. So you can clearly see the amount of data, like you can see around 211 million video starts. These are some of the practical usage of cloud and across different industry domains. So today we're going to talk about some of our experiences in dealing with the massive scalability requirements that are put on cloud from various enterprise applications. So there are 4 things that I'm going to talk about today. The first one is the scalability requirements from the cloud platform technologies themselves. I'll talk about multiple technologies in cloud. And then we also talk about the impact of how you can actually change the design and architecture and tuning of the applications that will have an impact on the scalability. And then we'll also talk about some of the open community because as more and more technologies are becoming like open source, and if you look at any cloud, whether it's IBM Cloud or Google, you can clearly see lots of the fabric components, whether it is monitoring, whether it is orchestration, everything is actually open community. So we do work with the open community to improve those frameworks for the massive scalability requirements too. So what credentials I got to talk on this subject? I'm an STSM and the engineering guild leader at IBM. I have worked on multiple performance engineering projects, right from the Intel and IBM Power Core design to the Watson IoT, Watson AI services performance and scalability requirements. And I also co-chair jointly with Mandar from Google the Istio Open Community Project and the performance and scalability work group. So today's topic, as I said, we're going to talk about Cloud Foundry, Kubernetes, Istio, and many of the open community technologies, how we are actually making those technologies better in terms of identifying the basic scalability requirements in multiple components, and how did we find them. And mainly we're talking about the enterprises. IBM being focused on the enterprise customers, we'll be talking about multiple customer scenarios today. We already talked about weather, the requirements that we need on the weather API. And then we also have healthcare. One of the use cases that I'm going to talk about today on healthcare, we need to support almost like 7 million consumers, the whole of California, both Southern and Northern California, for this particular healthcare provider. What kind of problems that we have seen to scale to that level, and what we exactly did, both in the open community as well as the platform and the application. Then we will move to banking, because banking also, if you are a banking customer, and then if you want to just go and look at your summary, account summary, or any of the moving the money or anything, banking has a specific set of requirements that will put on the cloud providers. And so what kind of things that we have uncovered there. And then we'll move to airlines. Because if you look at one of the major airlines that we are working on to scale their solutions, they have 6,700 flights per day, flying to 350 destinations. So we have different channels, like you have the web, mobile, and kiosk. So all these solutions, when you're accessing them on the cloud, there will be significant scalability and load on that, and what kind of issues we are looking at. And then we'll move to car rental. Like, if you and I go to like a car and try to rent it, so the whole experience of renting, both you go to the car and go to the kiosk, or an online, or through a third party, all these different channels, reach to the same cloud, right? So how we're actually solving those problems. And then we will get into consumer appliances, then maybe like washers, dryers, and different IoT devices that we have. All of these, you can see the variance in how cloud is being used in multiple industries. And I would like to share some of my experiences working with all of these domains. So if I were to sum it up, if I separate it out and then consolidate and then say, okay, what are those common things that we have seen across the industry domains? They are cloud platform fabric centric, because cloud fabric itself needs to mature to support this level of scalability. There are two aspects there. One is the fabric or the technologies themselves. The second one is the topology, how these things are put together to offer a cloud solution as a platform. The second one is the application design centric. So it's not always the cloud platform that you deploy to, but also when you move from an on-premise data center to a cloud, your application needs to be architected and designed and tuned for this massive scalability. So some of them will be, most of the applications are a BFF nowadays, like a backend for front-end design. So there are a few design best practices that you need to follow to support the BFF microservices. And then the second one, as more and more customers are actually going from monolithic to the microservices, one of the major things that microservices offers is Z-axis scalability. Like we know about X-axis scaling and Y-axis scaling, but microservices provides the Z-axis scalability. So that's the value proposition. So how are we actually working from an application point of view to achieve that? The third one is the performance governance model. Like as I have seen, all these are enterprise customers, so they have different lines of business. There will be a cloud, maybe CTO office, but they have to really work with various lines of business to provide the cloud resources for them. So there is normally, there is a governance model. They will specify, okay, what kind of runtime framework you're using. Maybe you're using Java or Node. Okay, maybe Java, if you're using, these are the limits for the memory that you can allocate for your instance. If it is Node, yeah, it is a little bit less, right? So those are some of the things that we need to look at from a performance governance model. Then most important thing is the data. Because all the applications, they interact with the different data services, which themselves are in cloud. So your application is running in cloud, but that is accessing the external data service. So that's, there are some best practices when you go from, like a previous legacy data structure to the cloud data service. There are a few things that you need to understand. And other aspect is the runtime framework. Because if you're using multiple, like maybe Go runtime, Python, or Java, each of these runtime frameworks, when these applications are deployed on these runtime frameworks, those frameworks have some strengths and weaknesses. So we need to understand, and sometimes you need to fix those runtimes also to enable your application to scale to that level. Of course, the last one is the network, because end of the day, when you look at cloud is nothing but a big, massive network, right? A network of computers. So you want to make sure that you take care of the latencies and the different, if you look at the front door, for instance, right? The request has to go through multiple hops to reach your application, which is either in Kubernetes or Cloud Foundry or wherever it is, right? So the front door and latency is very important for your overall application latency and scalability. And not only the front door, but also the back end when you get the egress traffic, when it goes from your application to different services. It may be a Watson IoT service or Watson AI service, or it's a data service. The latency of those hops is also really important. That's where some of the things like enabling the caching, for instance, to reduce those additional latencies. So let's get into the first one, the car rental. Most of these enterprise applications that I'm talking about, I was actually personally involved in all of these. So you can have any question, I can actually answer those. This is a kind of a journey, as when this rental company came to us, the main ask was, okay, we want to get this car rental experience to cloud. Right now we are running on some VMs on our data center, and we're using the SQL database, like the traditional legacy databases. But okay, we want to get to Kubernetes, we want to get to container, and then we also want to go from SQL to NoSQL. And what we wanted to do, as you can see, they wanted to have a multi-cloud strategy as well. So they just don't want to put just one cloud, they want to have multiple clouds. They want to show that we need to have the multi-cloud data replication as well, right? So, and the main ask was, okay, can you show us around 2,400 updates per second, 3,000 B-tree searches per second, with the response time of less than 200 milliseconds. That was quite, because you have so many degrees of freedom that are actually open, and you, first of all, you're going from SQL to NoSQL, and then you're going from an on-premise to containerized, and then you're going from non-cloud to a cloud solution. So these are some of the things that we initially came up with, so many obstacles to achieve the level of performance the customer is asking for. At a high level, this is the application architecture. You can see you have a rate reader service, and then you have some cache service to reduce the latency, and then finally the actual data is in cloud, NoSQL database. Of course, it has to interact with the customer's on-premise data center, which is almost like 200 miles away. So what kind of things that we have seen initially? When we put this solution, we were nowhere close to that 2,400 updates. We were like around 8 to 9 updates per second, nowhere close to 200 milliseconds. We were at 6,000, 7,000 seconds. It's like there is no, it's not that we can just tweak something and then we can achieve that thing, right? So from that point, then we thought, okay, it may be an IBM cloud. Okay, let's move to Amazon. Like, let's go to AWS. It may be a cloud issue. And you can see in this chart, it's nothing to do with any cloud. So you can see the same kind of performance, whether it's AWS or IBM cloud. So then we stumbled on the real data structure. How are we actually doing? Because what happened was, when we're moving from SQL database to the NoSQL database, we just used, I'll show you the data design here. So we had like, 5, every that table, like, we just made it as a different document, and then, we are actually doing like kind of 5 queries to get to the data that you need. That is, you can't just directly map from your SQL to the NoSQL with the the old schema that you're familiar with. That's the fundamental thing, because you have to do from 2 different tables, you have to merge that, get that part, and then you go and query in 3 other different tables. That was the one that was really getting to us, and then we changed that whole thing to a document DB NoSQL specific design, how you should exploit that. Basically what we did, we removed those 5 queries and just made it as one query, just a single user data table. So you design the document such a way that all your data that you're looking for should be in one document rather than spread it across in multiple documents and then get them and then correlate those data points. It will work, but for the level of massive scalability that we are looking for, it won't scale. And once we change that, you can clearly see not only that we were at 810 updates per second, that has gone to not 2400. We are able to show almost 5000 updates per second. And then queries were significantly higher. Of course, here in our testing, we encountered a specific, the FortiGate 300, that was like 1 gigabit. So the network latency was the one that we were able to get to 1200 from 9 searches to 1200 because of the network. Once we changed that from 1 gig to 10 gig from FortiGate, yeah, we were able to get to 3000. In fact, we exceeded the goal. So these are some of the things that we have learned. And not only this, as part of this, we also had to redesign our ingress controller. Our container service ingress controller was not scaling either for this level of scalability. So we redesigned our ingress controller for our Kubernetes service, IKS, and that, in addition to the data change, that gave us the requirements from the customer that what he is looking for. Now let's switch gears to consumer appliances. So this is like kind of this customer, they wanted us to host because they want to, let's say you have an iPhone or Android phone. You want to control your laundry, your dishwasher or dryers or microwave. All those things with Watson IoT, they wanted us to showcase those APIs accessed running in IBM Cloud. And they want to show us, okay, they asked us to show, okay, can you show all these APIs to perform less than 500 milliseconds? That's the latency. That's the main thing that they asked us. And initially, we used Cloud Foundry as the architecture. And then we used the Maximo and stuff. But later on, we realized, okay, let's move to containers, right? So we moved to the containers. And this is the architecture with the MTM platform. So you can see the washers and dryers with IoT devices there. And then you end customer with his iPhone or mobile. So there are multiple hubs. You have the Watson IoT that hold with different partitions, and then you have the message hub with the different topics, and then you have to have multiple components, multiple services like Redis and Data Store, Message Hub, all work together in sync to get that 500 milliseconds. So if I were to change this and put it as a performance-centric diagram, you can see this is how we divided this into different partitions in the Watson IoT and then mapped them to the specific one Message Hub. So what it does is it gets the hex-centric messages from the IoT devices, and then we actually map them and turn them to JSON objects, and then we send them back and then put them on the Message Hub. And then there is an application that is actually deployed on Kubernetes service in IKS that will pull those data points. So the main issue that we have seen here was the lag. If you look at, we designed a Grafana dashboard to really visualize what is happening under the covers as you scale the solution. What we see here, if you look at the lag, lag is the queue, how the queue is actually queue size is actually increasing, because the system is not able to remove the message and process them in time. So we had to really tweak the Message Hub partitions and the IoT message queues there to reduce that lag. And then we were able to showcase 500, we were able to actually get to like 380 milliseconds. So this is entirely different from the car rental stuff, and now this is with IoT and then IKS and stuff, right? Here also we had to deal with the front door scalability. So the front door has to be redesigned, and we have used that to get this one. And now let's shift to banking. So banking, of course, as you know, banking has restrictions, so you can't put it on the public cloud, but here we use the private cloud. Again, we used Cloud Foundry to do this. We have this particular customer is already having like 70 applications in production across different lines of business. But I would like to share our first Sprint Zero when we started with retail banking. That's where we started first, and then once we are successful there, then we launched and scaled it to different line of businesses. So what was the ask for the retail banking when we went to the Sprint Zero? That was mainly, as I said, is Cloud Foundry. So they have a traditional WebSphere middleware kind of an application that's already running. They want to get it to cloud. So what we did as a Sprint Zero, we took three parts of it. We took the security, UI, and the service integration. Those are the three parts we took, and then said, okay, we're going to put these things into cloud. And then rest of the middleware services, they still remain on mainframe and backend. So what we did, we tried to expose those things as different APIs, and then call those APIs from within the cloud, these Node.js applications that we have, and also AngularJS is the one that we've used. And then they're using, of course, mainframe. And they had some security. I think if you're familiar with the security that we have, that Trust Association Interceptor that we use to do the authentication part. So initially what was happening was they asked us, okay, can you show us 500 to 600 transactions per second? And we were at around 12 to 15 transactions per second, and they're asking sub-second response times. Sub-second response times, we were nowhere close to that. We were around like 20 to 30 seconds response time. So then we went from that 12 to 15 transactions per second to customers ask of 400, no, not 400. We showed them almost like 900 transactions per second. And yeah, we were showing at 700 to 800 millisecond response time. How did we do that? There are multiple things that happen. Again, we have Cloud Foundry Fabric itself that has problems. We'll talk about that. And then the second one is the cloud infrastructure itself. And then application itself has some issues like sticky sessions and stuff like that. So let me get into the first one. So this is where we identified the Cloud Foundry Fabric. As you push an application, because Cloud Foundry, when you push an application, it will stage that application using a deployment model, like the model that we will do as a droplet. So you get the droplet, and then the droplet is the one that will be deployed in the specific runtime that you want. It can be a Java build pack or a Node build pack or Python, whatever runtime you want. But the Cloud Foundry, the way it runs is actually, it's not a flat file system. It is it's not a layered file system. It is a flat file system. So because of that, what is happening was you had the droplet size increased significantly. So the bigger the droplet size, the more CPU intensive operations you will have, because end of the day you have to uncompress, compress the droplet size, and then get the elements in there, and all those things are high CPU intensive operations because you have big integers involved and everything, right? So what we did, I worked with the Cloud Foundry community, said, oh, this is not the right architecture. So we agreed on removing that architecture of the build pack. We have architected the build pack mechanism to remove that flat file system and then introduce a layered file system like Docker. This is called the OCI build pack that we introduced. So that has significantly reduced the size of the droplets, and then the CPU spikes that you were seeing previously, the CPU spikes of almost 250, 300% CPU, all of a sudden that has come down to 50, less than 40% CPU. So that has increased really the stability of the system. And then another thing that we have come across is the runtime framework. The Java scheduler that we're using in the Java build pack that we are using, that is really not able to cope up with the mainframe backend latency, because typical mainframe latency is around 200 to 150 to 200 milliseconds. But when that latency increases for whatever reason it is, then you clearly see the runtime framework is not agile enough. So there will be a big queue up, so it doesn't scale at all. So we redesigned that scheduler to allow for the cloud scenarios where you can't really dictate the backend service latency, right? So we redesigned that. That has clearly opened up. You can see 7x improvement just because of that. So now let's get into airlines. Another airline customer that another industry that we focused on in airlines. Here you can see on your right-hand side there, that is the original design and architecture. You have they have the Tomcat web servers and traditional architecture. And then we changed that whole thing to a BFF, backends for front end, and that enabled us to serve for multiple clients, multiple client types, and really refactored that whole traditional architecture. But that came up with that posed some problems for us in the BFF redesign of that whole thing. Some of the issues that we have seen is the very high CPU intensive microservices, so we had to deal with that. And then we had the socket timeout exceptions, as your applications are actually reaching out to the public cloud and accessing this the different services like ESOVA services that we have seen earlier. We had issues there. And then auto scale issues, and then of course we had the excessive CPU capacity that we have seen there. Some of them are like you have seen already on the push, the CF push, and resulting CPU spikes that also contributed here. So here what we did, again there is a fundamental architecture issue that we have identified in Cloud Foundry, because Cloud Foundry, what it does is one of the major things that will impact the latency on the Cloud Foundry is when you have a microservice. Let's say you have two, service A and service B. Right? Service A cannot directly talk to service B. Even though you are invoking A is invoking B, the service has to go, that call has to go all the way out to the firewall, then gets into the proxy, and then gets into the Go router, and then get to the application running in a Diego cell. You see how many hops that you have. So as you scale the application, definitely all these hops are going to add it to it. So what we did, we worked with Cloud Foundry to replace that with a new feature called container to container. So container to container with the Silk CNI plugin, what it does, you can see here on your right hand side. So you can define some policies. Application can, at the application level, you can define some policies. Say, okay, application A can directly call B, or application A can call C. You can also say, oh, B cannot call C. So all those policies significantly reduce the latency for us. And you can clearly see this is one of the chart that shows without the container to container and with container to container, almost 2 to 3x reduction in the latency. So this is another thing that we have driven to this one. So, and then from a BFF point of view, as I said, we moved the architecture to the BFF. One of the things, because people who are familiar with the traditional languages like Java, C++, they're familiar with synchronous programming, whereas Node.js is like a little bit, asynchronous, like you use that for I/O intensive applications and stuff. So the developers try to force using the promises to make that Node.js programming model to be asynchronous, which it's not designed for. That has caused the scalability issues. And then the second one is Node.js is a single threaded. So you cannot have, even though your application, your container may have like 4 vCPUs, you cannot really consume that CPU capacity because it's a single threaded. So you need to scale horizontally. So that's another thing. So these are some of the things that we identified. Now let's move to the healthcare. Healthcare, one of the main customers that we have worked on IBM Cloud, they have the pharmacy center, appointment center, message center, all these different lines of business. They want to move their traditional applications to IBM Cloud. And they asked us, okay, can you roll this solution to 7 million in California? Right? So and then we have a specific latency requirements. We want to make sure that there is no long tail latency. And some of the things that we have encountered initially was the long tail latency. Then the capacity issues again, lots and lots of microservices design issues, because now it's a typical hybrid cloud scenario. You have a native cloud application going back to the data center, and you have traditional middleware pieces all stitched together to provide the final customer solution. So here also, this is a high-level architecture. You can see this. There are multiple things. It's a typical any enterprise. You can see that, right? When you just log in, right, and it goes through a portal. That's your portal, and then it gets that data. And then once you get the dashboard, you go give your credentials, and then get into the data power. And the data power API, it'll get a microservices call into the cloud native pieces in the IBM Cloud. And then from those applications, because they will be calling a legacy EIS services, which are again on-prem, like the electronic medical records and all those things. So you can clearly see it's not just the cloud native piece, it's not just the front end, but the back end, the systems of record. So with all this complicated architecture, you need to make sure that the solution will get the latency for the 7 million customers that we have. So we have encountered many things there here. The first thing, the backend service. So the backend service latency, if you have the backend service latency, that is a number one inhibitor for any scalability part. And then the second thing is the database schema. So we added some caching layer to reduce the round trip costs and stuff. And then the database schema, again, they use the BCNF. They are coming from the traditional SQL to the NoSQL, but still they stick to the BCNF data schema instead of sticking to DDD, moving to DDD. That is another one that became a big inhibitor for us to scale. Here you can see how the backend service latency will impact the scalability. So the backend service latency, as you increase from 100 milliseconds to 500 milliseconds, you can see the reduction in throughput in the first chart, and you can see the latency increase there. And how the BCNF and to DDD change from a data schema, how that's going to impact significant changes. You can see that almost 2x improvement just by changing that from BCNF to DDD. And then another issue we have seen, which is a typical thing for any microservice application, is the long tail latency. Long tail latency is, for some of you who are not familiar with it, long tail latency is the difference between an average response time to your 99th percentile response time. If it is like significantly higher, then you have a long tail latency, because some of your customers will see a significantly higher latency than the average thing. So long tail latencies are very tough to solve because there are multiple things. It can be a network, it can be an application, it may be caching, it may be backend. So there are so many things that can impact the long tail latency. One of the things that we identified here for the long tail latency is also a Cloud Foundry specific design issue. they have a Go router doesn't support the keep alives. So then we worked with the Cloud Foundry to enable the keep alives, for redesign that Go router to enable the upstream keep alives. That has significantly reduced. You can see the long tail latency come down. And again, from a capacity point of view, you can see initially when we had those performance issues, all the cells were like kind of 80% to 100% full. We have optimized, we did multiple optimizations to bring those things down to less than 25%, average 25%. That is another thing that clearly stabilized the whole system to allow us to get to roll out to the 7 million customers. So you can see a pattern from all these things, right? So what is happening is there are multiple cloud-centric open community projects that we really work with. As I said, I'm the co-chair for the Istio, Performance Scalability Workgroup. So we have lots and lots of performance issues that we're actually right now working to make sure that all these enterprise customers will get the required scalability. And the Cloud Foundry also, we have two things we're doing at Cloud Foundry. We're hardening the current architecture and replacing and doing some kind of re-architecting some of the pieces. But also at a long-term stuff, like I'll show you, we are completely re-architecting the Cloud Foundry. And basically what is happening is Istio, Kubernetes, and Cloud Foundry, they all will be working together in future. So I'll show some of those things as well. And in Istio, I'll get to what we are working on. And then on Kubernetes, for instance, Kubernetes also, like you have a lot of things to do. Kubernetes, of course, is a nice pluggable architecture. So you can, if you don't like a specific piece, you can take it and you can have another one. One of the pieces that we are looking at is the scheduler itself. Scheduler is not right now, to be honest, I don't like the current default scheduler because it doesn't really understand the stability issues. If a specific cluster is unbalanced, it cannot, once it puts the parts in the different nodes, it cannot really readjust that cluster to bring that unbalanced cluster to the balanced one. So what we are working right now is, from a community point of view, something called descheduler. It will try to kill the pod if it is on a node which is like highly CPU bottlenecked. But that is also not really cutting it. So internally we are working on another thing called smart scheduler, which will take into consideration some of the runtime characteristics and then try to dynamically balance the cluster. So if you look at the Cloud Foundry specific, there are multiple layers. You have routing, networking, build packs, CPU shares, sidecar support, multiple schedulers, and service mesh. All these areas we are actually working with closely. I'm part of the Cloud Foundry community as well, trying to get these pieces, fix the routing issue with the Go router keep alive, fix the networking with the container to container, fix the build pack issues going from a flat file system to the layered file system with OCI. Use the CPU shares, because right now it doesn't really consider the memory into consideration when you're actually giving the CPU shares to different containers. So we're actually changing the algorithm to fix that. And right now you don't have, the Garden containers in Cloud Foundry doesn't have a pod-like architecture. So you can't have a sidecar. So you can't really support Istio. So we redesigned that to enable that to a pod-like, so you can actually have a sidecar, Envoy sidecar there. So we have multiple schedulers now, right? And we have with the CFE product, so you have a like a Kubernetes scheduler and the Garden scheduler. We're actually working to replace those things too. So as I said, just to sum it up, these are the Cloud Foundry optimization features that we have driven, mostly from all these enterprise workloads that we have worked on. And then from a container point of view also, we have identified many things. For instance, when we were going from DES to Diego, we were not able to go beyond 30 containers in a 4 vCPU VM. And we were clueless what was happening. And then what we saw with our soft layer VMs, we get by default a para-virtualized VM, the VSI. Then we changed that to HVM. All of a sudden, you could see from 30 containers to 200 containers in the same Diego cell. So things like that from a container point of view, and then redesign of the scheduler stuff, and also the front door, and then multiple things from a Fluentd, and then other optimizations like the autonomic Java scheduler redesign. So there are multiple design changes that we need to look into, not only the data design, but also the platform specific things that we have worked on. So now let's quickly get into the Istio, because Istio is, as more and more people are getting to microservices, as the number of services in a bigger microservice application are increasing, it is very difficult to manage, and also it's not fair for the developer to do all the plumbing work, like whether it is the routing, load balancing, resiliency, and security, and all that stuff. If you can take the developer off of those duties, let the service mesh do all those things for you, then the developer can focus on his specific domain. If a banking or healthcare, he can put more differentiators from a business point of view, don't need to care about the rest of the stuff. That's exactly the reason why service mesh is actually getting ground. And really, when IBM, Google, and Lyft started this service mesh last year, Istio, from just 1 year, you can clearly see the significant how much the Istio is getting more popular, and more people are actually using. But we have some work to do. So from an Istio service mesh point of view, basically you have two things. You have a control plane and you have a data plane. A data plane is where you have the intelligent proxies sitting next to your services. And then control plane, you have a pilot that controls how the traffic should flow to the sidecars with different configurations. And then Mixer will provide you the telemetry, it will provide you the policy support, all that stuff. And then you have the Citadel with the certification management stuff, right? So we focus from a performance and scalability work group point of view, we focus on both the data plane and the control plane to make sure that the whole mesh is actually architected for performance. We applied the Istio service mesh for an online banking I just showed you. And then we identified, okay, when you put Istio right next to this, how the path length is actually distributed, how much additional CPU you need to support the service mesh. When we started that initially, that was really high. Then we started working on multiple things. We are right now working on sidecar optimization with Envoy, pilot optimization, and we are introducing many things in the Mixer. So what exactly we are doing? We are also in that process. We are giving the end customer of the mesh a clear view of how much resources that they need. And you can see ingress and telemetry and sidecars. For getting 1,000 requests per second, how much additional millicore CPU you need. So you can actually do the capacity planning and stuff there. And then not only we just left with that, we have updated the Istio dashboards with all of the data points there. And then we have an Istio SWAT team that I'm co-leading with Mandar from Google. You can actually go and see this. There are multiple, around 14, 15 different things. We have multiple epics. Each one has multiple GitHub issues. So this is a work in progress, and our plan is to completely re-architect and then optimize this mesh so that it can be easily used across the enterprises. Towards that, as I said, this is the dashboard that we have introduced, the data that you get from the Prometheus, and then we push it into the InfluxDB and get it on the Grafana dashboard. You can see the vCPU per 1,000 requests. And then we also have an integrated dashboard that we have as part of this. This will help you multiple dashboards in there. Everything is in one area. This is the Cloud Foundry, the future version, how it's going to transform Cloud Foundry. You can clearly see we are addressing the north-south traffic, east-west traffic, and also the security integration. So from a north-south traffic, we are planning to replace the Go router with Envoy. For the east-west traffic, that's with app to app, we are introducing the Envoy, like a kind of a sidecar stuff there. And then that's exactly where we are also thinking a project called Irene. What we are trying to do, we are trying to replace that Diego scheduler with the Kube scheduler there. So because Cloud Foundry is good for as a PaaS platform, it's pretty good for application development. That is a CF push. We are going to keep that experience, and then scheduler we take the Diego and then put the Kube scheduler in there. So with that, I want to sum it up. For getting the scalability that all enterprises are looking for on cloud. So we have significant improvements and design changes in the platform scalability and microservices scalability to exploit the Z-axis scalability and the service mesh usage. And then the data scalability in terms of the right data selection and the data schema selection. And then the community framework, multiple features that that community, cloud community offers. And then the service integration scale, again, we need to make sure the network specific things. And then each industry has a unique characteristic and unique kind of the application pattern. So you need to understand and actually code and use it in that aspect. So that is my end of my, so any question answers? Any questions that I can answer here? How many of you are actually using Istio right now, like at least experimenting? Okay, good. Anybody on Cloud Foundry? Kube? Okay. Oh yes, Istio, right? Yeah. Okay, so the question is, I told about Istio. We have come up with some dashboards that will tell you the capacity, how much capacity you need to do 1,000 requests per second for a specific thing. What we are doing there is actually we're doing three things. We want to distribute that among the Istio components, like ingress gateway, telemetry, and sidecars and stuff, so that you can pick and choose. We have actually come up with something called Istio Lite, like kind of you don't need to have the whole mesh. You can choose, pick and choose. So based on this data, and then you have the dashboards that will tell you exactly how much you are actually using in those areas. So that will make you like a more of an informed user of the service mesh. Yeah, okay, so for database design, how did you change the data? Why did you find in the first place? You need to change the data schema. Yeah. Yeah. So initially, like as I said, right, we didn't really look at the data schema as the issue, as we thought initially it's the cloud platform is the issue, right? That's why we changed from IBM Cloud to AWS, and that's it. No, we didn't see anything. Then we looked at, we had multiple internal tools that we have used, but also we tried to correlate the transaction. Right from the beginning, like, basically it's a rate application, right? So when we are correlating the transaction, what we saw was nothing is that much latency you didn't see in the platform itself, but the call that you make to the backend, we saw that is significantly taking more time. And then we started looking at, we divided that as searches and updates, and then we started looking into the B trees and, are we doing queries, are we doing lookups, and then we get into the best practices for the Cloudant that we have used. I think we are at the end of the time now here. Thank you very much.